Okay, so we are now going to look at the alternative to practical part of the paper. With this, it is not testing your understanding of physics, it's actually testing your ability to engage with the practical, so to understand methods, evaluate information, and draw answers from that. So you need to approach this in a logical way, which of course you do for the rest of the paper, but it is much more about your reasoning than your prior understanding. So if we jump forward to that, our first few questions are pretty simple, right? So for question 1, there's a lot of information here, and I'm going to make sure I read all of it in my exam, because this is going to provide my understanding for completing this. So some students are investigating how the volume of water affects the rate at which water in a beaker cools. They are using the apparatus shown in figure 2.1. So it's here, and I know that it is about cooling. Okay, so that's important. At 200 centimeters cubed, hot water is poured into beaker A, that's this one, and the initial temperature rises to a value shown on the thermometer, which is here. In the first row of table 2.1, which is down the bottom of the page, down here, it asks me to record the temperature theta A at time equals 0. So I'm going to do that straight away. So I am looking at here, and it is between 80 and 90, and there are 10 increments, so it must be going up in ones. So I've gone 1, 2, 3, 4, 5, 6, 7. So my answer is 87 for that one, which as it looks, you can see from the data that's about right because it's following the pattern. Next one, 100 centimeters cubed of hot water is poured into beaker B. The temperature rises to the value shown on thermometer B at figure 2.1, so that's this side. In the first row of the table, record V to B for time equals 0. So same thing. So I'm doing the same scale, and it's got the same increments. So this time I've gone 5, 6, 7, 8, 9. So it is 89 for this one. That is my first mark done. For the temperatures theta A and theta B, the water in each experiment at times 30, 60, 90, 120, 150, and 180 are shown in the table. Complete the headings and the time column for this table. So let's do headings first. The headings are already there, but you can see they've got the letter showing what it's measuring. So T is time, theta A and theta B are temperatures, then it's slash, and it's left space for the unit. So I need to put the units in here. And it's told me the units in this information, right? So the unit for time, it said is seconds, so I'm just going to put an S, or I could write seconds, either is fine. And I'm recording temperatures, so I'm going to try and be logical about this. It's a thermometer. I've not ever seen in physics any thermometers that measure a scale other than Celsius. The other thing that is logical is I'm using water, and I've said that it's hot water, so hot water should be kind of in the top end of the 80s, 90s kind of temperature. So I can tell that this is Celsius, right? If it was above 100 Celsius, it wouldn't make any sense. If it was Fahrenheit, for example, this would be like body temperature. It wouldn't even be hot. If this was Kelvin, this would be freezing cold. It would be it would be a block of ice. It wouldn't be water. So I know this must be Celsius. So I'm going to put a C and a C. Technically, I should put a little circle to say it's degrees C, so I'm going to do that. I now have that for the first mark. The second mark is I need to put the times in. And it told me the times in the question. 30, 60, 90, 120, 150, 180. So let's put them in. 0, 30, 60, 90, 120, 150, 180. Done. 2 easy marks. Good. Question B. Describe one precaution that should be taken to ensure the temperature readings in the experiment are as accurate as possible. Now, it's very tempting with this question because it says precaution to think it's talking about safety. It's not. It's asking about accuracy. So I want to say something about this experiment which is going to affect my accuracy when I'm reading the temperatures. Okay? So it's something about the way I read this information here that's going to tell me if it's an accurate reading. So it is tempting to talk about repeats and things like that, because that's how you generally improve accuracy, but it's not how you improve the accuracy of a specific reading. To do that, it's about the way in which you take the reading. So you should be talking about, how do I read this thermometer so that I know I'm reading the right number? So the answer I would give is to get down to eye level. So you're reading it at eye level, or you're reading it from the meniscus. So I'm going to put that, reading at eye level. Okay, that is my answer there. There's a few different choices for what you can have. So if you said you're reading it at eye level, reading the meniscus, if you're reading it at a perpendicular angle or at 90 degrees to the thermometer, that's fine as well. Or you can actually have making sure that the reading is taken from the water correctly. So if you talked about, say, stirring it, that would have been correct, because that's distributing the heat out to make sure it's an accurate reading of the whole water. Or if you said you would wait until the thermometer stops changing, of course, that should be one as well. Okay, so there's a whole choice there. My one would be to think about, well, it's talking about reading, so how would I read a thermometer? Question C. Write a conclusion stating how the volume of water affects the rate of cooling of the water. And it says, justify your answer with reference to the results. It's 2 marks. So it's going to be 1 mark for the conclusion and 1 mark for the justification. Okay. So my conclusion, looking at this data, is the temperature is going down as time passes, right? So that is the entire question, isn't it? That's what we're investigating. So I need to be saying that as the time passes, we're investigating the volume, right? So this is what I should be doing. As I was just doing there, you should be reading back, checking what it's about. So we're investigating how the volume of water affects it. So we're saying, how does the volume affect this? And I know that beaker A has a larger volume, beaker B has a smaller volume, and I can see that beaker A has cooled down more slowly because it's only gone from 87 to 77, that's about 10, and the other one has gone from 89 to 74.5, so that has gone down by about 15. So my conclusion is that a beaker with more water, or a greater volume of water would be fine, with more water will decrease in temperature at a slower rate. So that is my first mark, that is my conclusion, but I still need to justify it. So now I'm going to say that beaker A with 200 cm cubed cooled by, I checked the total, it is 9.5 degrees centigrade in 180 seconds, but B with 100 cm cubed cooled by 14.5 degrees C. Done. I've got this section telling me my conclusion, this section making a comparison from the results to prove that. Question D. I've been given an equation and I do not recognize that equation, so I need to make sure I'm just using it in the way that I'm instructed to. I'm not going to worry about what it actually means, right? So, using the result for 100 centimeters cubed of water, calculate the average rate of cooling x1, so that's telling me what this equation is. The equation is the average rate of cooling for the first 90 seconds, so the first 90 seconds, not just any 90 seconds, it's that first bit, use the readings in the table and the equation. Okay. So this is for the 100 centimeters cubed we're going to do. So I'm going to look at here now. So it's 100 centimeters cubed. It is this column. And I'm going from 0 to 90. So it's from this one to this one, 89 to 80.5. So I'm going 89 minus 80.5 divided by the time, which was 90. So if I put these numbers through the calculator, so 89 minus 80.5 is 8.5. Divide that by 90 is 0.094 recurring. And it says in the question to include a unit for the rate of cooling. So my answer then, I should be putting 0.094. That's enough decimal places. And then I want to put a unit. Now my calculation was a temperature change divided by a time. So the unit for temperature change is Celsius, and the unit for time is seconds. I divided by seconds, so I put that there. So I can see that the unit is degrees Celsius per second. Degrees Celsius per second. You have to have the answer and the unit to get the marks. Question E. A student suggests that it is important that the experiment be done with 2 volumes of water that should have the same starting temperature. State whether your values for x1 and x2 support this suggestion. Justify your statement with reference to results. Okay, so we need to be using our results to work out an x2 to then come up with a statement. Okay, so if I look at this data and I look at that first 90 seconds, I have got a temperature change of 8.5, I just said, but that means a cooling rate of 0.094. What I want to do is show that if I start at a different temperature but have the same volume, so my starting temperature is the only difference, that it's going to have an effect. So what I want to do is I want to look at the same column again, because that's still got the same volume, and I want to pick a different 90 seconds to see if it makes a difference. So I'm going to pick the last 90 seconds now. So I'm going to go from 90 down to 180. So I'm using 80.5 and 74.5. So if I do the same calculation, so 80.5 minus 74.5 over 90, if I do that calculation, I go 80.5 minus 74.5 is 6, divided by 90 is 0.067, if I round that to 2 decimal places. So I can see that if I have a lower starting temperature now, my rate is lower. And I can know that is reliable because I have used the same beaker of water. So I know that the volume was the same, the materials were the same, everything else about it was the same. It was just that temperature that was different, right? So that means I know that it's important to keep the volumes of water the same. So it is important, so not the volumes, the temperatures. Important to keep the starting temperatures the same. So x1 has a rate of 0.094 Celsius per second. So that's my x1 statement, which I asked for here. But x2 from 90 to 180 seconds for beaker B is 0.067 Celsius per second. So now I've explained x2, and I just need to tie this off by saying, how does this justify this? Okay, so the different temperatures has affected the rate. Done. And that's a big answer for 1 mark, but it's asking you to do all of that, and you have to have actually done that to get the 1 mark. So that is your answer there. I've made a conclusion based on the table and the previous information, plus this equation here. Okay, so I'm using that equation to make an assumption. The second question in the alternative to practical section of the paper is to plan an investigation. So, a student is investigating the factors that affect the size of a crater, which is the hole made by a ball, when it is dropped into sand. Plan an experiment which enable you to investigate one factor which might affect the size of the crater. So only one factor. Okay, that is very clear. If you're talking about more than one factor which might affect it, you have to make sure those other factors are controlled. If you suggest more than one factor, you're not going to get the mark for that. So the apparatus available includes these 2 things. So we know that these 2 things are available. So I should be thinking about how I'm going to use those in my investigation. I need to write a plan which should state the factor being investigated, state the key variables that we control, any additional apparatus, so anything other than these 2 things that you would use. I'm going to explain how I would carry out the investigation, including what would be measured. Okay, so that's our third variable, and how you would do this. Right, so that's asking for quite a lot of detail in that method there. You would state the precautions you would do to attain reliable results. So again, that means precautions in terms of accuracy, not in terms of safety. And finally, we're going to suggest a type of graph that you would use for this. So it's a suitable graph. Okay, I've got there 1, 2, 3, 4, 5, 6 things, and it's 7 marks. So I should be immediately thinking, well, I need to include all 6 of those things if I'm going to get the marks. And one of those things, there must be an extra mark in there somewhere. Okay, so let's start with our 3 things here. Okay, we've got the 3 types of variable. We've got the independent variable, the control variables, and the dependent variable. Straight off the bat, I'm going to start by naming those things. And I'm going to write this in a way that makes it very, very clear to the marker, the invigilator, the examiner, what I am doing. Okay, there is no harm in drawing attention to the different parts, so I'm going to do that. So I'm going to go variables, really clear. So then I can go independent variable, and I'm going to say, so I had a choice, didn't I? I had to choose something that is going to affect the size of the crater. There are 2 possible things that can affect the size of the crater. It is either going to be the mass of the ball, or it is going to be the height the ball is dropped from, right? Because that height is then going to make the ball fall faster, and it's going to hit with more force. So I can choose either of those 2 things. My choice is going to be the height, because in my head I can already think how that is going to be easier to control, how I'm going to measure that, and there's less things that might be affected by the height, because I can change the height without having to change anything else. The mass of the ball I could also change, but if I'm thinking about changing the mass of the ball, I'm also going to have to think about, well, I still need to keep the same volume, which means the density is going to be the thing that's changing, and then I need to worry about how I'm going to keep the height the same the whole time, right? Which requires more description. There's nothing wrong with that. You can do that, no problem. But I'm going to pick the one which I feel is easiest to do. But when we go through this, I'll also explain how to do it for both. So you would write one of those there. I'm going to say the height above the sand from which the ball is dropped. Okay, and you can see I'm not just saying height, I'm not just saying drop height, I'm not saying height of the ball, I'm being really specific with my independent variable, which then means that there is no way they can be ambiguous with that answer. They know that I know what I'm talking about. So that's my independent variable. My dependent variable, the thing that's being measured, they've already said that in the question, it is the size of the crater made by the ball. And your dependent variable has to be that. There's no two ways about it. It's already told us that in the question. Control variable then, this is anything which may affect the whole size other than the thing I've chosen. So if I've chosen height of the ball above the sand, then I know that the mass of the ball has to be the same. So mass of ball. And of course, if you said that the mass of the ball or the density of the ball here, you should have said the height of the ball as a control variable. And again, be really, really specific that it's the height of the ball above the sand from which you are dropping it. So once you've said the mass, I'm also going to say the volume of the ball. That has to be the same. Of the ball. The shape of the ball. The type of sand. You could also say the size of the sand grains, or the moisture of the sand, or the stickiness of the sand. All these things would work as well. I'm also going to say the depth of the sand, because if it was only, say, a millimetre thick, that's going to have very little effect on the size of the crater. Whereas if it was, a metre thick, that's, it's going to have a big impact there. And you can see I've already got a list of 1, 2, 3, 4, 5 things there. You want to have at least 3, right? If you've only got 2, you probably get away with it just about, but it's unlikely. Minimum 3, I would say. If you can get more, put them in just in case one of them is wrong, right? You don't lose marks for putting the wrong variable in the control variables unless you contradict yourself. But you can always gain marks by putting the right one, right? And as I said, if you've put something in one of these two, so if you've said something is independent or dependent, it cannot be in your control variables. There were 1 or 2 people, I think, who said height as the independent variable, but then they also said height as a control variable. You can't do that because then you lose marks for both, because you contradicted yourself. So there's my variables. Next thing it asked for was the equipment I would need. So if I'm going to be dropping this ball from a set height, I need to know the height of it. So equipment, I know I need the sand, I need metal balls, and actually, although there's a variety, I can say 1, because I only need 1 for this experiment. If you were changing the size of the metal ball, you would obviously have more, and you should specify what masses you would use. Okay, for this I'm going to specify that it is going to be 100 grams and it is going to be 1 centimeter in diameter. Okay, that might not necessarily be true, I'm just making that up, but what I'm doing is I'm showing that I'm being specific. I'm showing that I know that the size of it is going to make a difference. If you chose the metal balls to be your variable that you're going to change, you would then of course say that all of them would be 1 centimeter diameter, but one would be 100 grams, one would be 200 grams, one would be 50 grams. You would specify specifically what that is going to be. Now, to measure the height of the ball, and this goes for everyone that does this, no matter whether it's a variable or not, is you are going to say a meter stick or a tape measure, but something to measure the height of the ball. Okay, and I'm going to say 2 actually for this, so 2 meter sticks, because I want to measure up to 2 meters in my plan. Even if you're keeping that constant as a control variable, you still need the meter sticks to show that it's the same height all the time. I also want something to measure the size of the crater, so any piece of equipment that measures a distance is going to be fine, but I want something that's detailed as possible, so at least a 30 centimeter ruler. A 15 centimeter ruler would have been fine as well. A micrometer would have been alright as well. Anything that's going to measure at least to the millimeter is going to be good. I am then going to move on, and next I want to look at the method. So I would say method. Step 1. I want to make sure that I am dropping the ball into some sand. Now remember that getting the equipment is not part of that. You can assume they've already got the equipment, but you want to make sure they're using the equipment properly. So I'm going to say place rulers, or place meter rulers, meter sticks, vertically end to end to measure height. Okay, measure height. So that's my first bit. Next bit, I want to make sure they're using the sand properly. So I'm thinking, well, I want the sand to be smooth, otherwise it's going to be bumpy already, and then that's going to be harder to measure. So 2, ensure sand is flat and even. Okay, so that I know I'm dropping it into a reasonable depth. At this point, I'm actually thinking, well, I want to make sure the depth is suitable, so I'm going to add into my equipment list sand, and let's make it 5 centimeters deep. I could say more, it doesn't matter, but I definitely don't think anything less than 5 centimeters would be appropriate. And that's the same for everyone again, so everyone should have been doing this, no matter what you chose as your independent variable. What I'm then going to do is I'm going to drop my ball, so drop ball from 10 centimeters height for remove ball from crater and measure the diameter. Now, you don't have to have said this, but I'm now thinking, well, is the diameter going to be the same in every direction? So let's say you're going to measure the diameter from the narrowest point, right? Across the narrowest point. And what I'm doing there is I'm just showing that I am aware that the crater may vary in size, so I'm planning for difficulties, I'm planning for errors that could creep in, right? So I'm showing that I'm thinking about error. Okay. Then for question 5, I've done it for 1. I want to repeat it. I want to make sure I've done it several times. So repeat, drop. Actually, I'm going to say repeat steps 2 to 4 more times. What that means is I've now got 5 repeats at that height, okay? And repeats are going to be a good way for me to show that I'm thinking about accuracy, and that is actually where that 7th mark comes in. Remember we said there were 6 points that you can get marks for? That's the 7th one that is not listed in the instructions. For questions for step 6 then, I'm going to say repeat 2 to 5 from, rather than 10 centimeters, I'm going to do 20 centimeters, 30 centimeters, up to 2 meters. Okay. I could have said it differently. I could have said in 10 centimeter increments up to 2 meters. I could have said a full list. Anything would have been fine. I could have even drawn a table if I wanted to do it that way. And that last step there, that is the only thing that will be different with your independent variable being the mass of the ball instead, or the density of the ball, right? Because that's the only thing you would be changing, is you would repeat it for different masses rather than for different heights, okay? And you may have chosen a higher height here because 10 centimeters is quite low, and I've done that on purpose in my height investigation because I want to move through a range of heights, whereas you would probably want to stick with something in the middle and then we'll change the masses. So that is now the different variables done, the additional equipment done. I've said a precaution to take reliable results because I've talked about the sand and making sure that the height is the same the whole time. So the last thing left to do is to do a graph. Okay, I don't need to draw the graph, I need to say what kind. So my data, I am talking about changing heights and I'm measuring diameters. Okay, so I know that this is two sorts of numbers, so I know that my graph has to be a line graph, or a line graph in this case, a line graph. Okay, and that would be the same for the changing the mass of the balls as well, because mass is a number, and you're measuring the height, the size of the crater, so that would be a number as well. So it would still be a line graph. Whereas if you just said small, medium, large, that might be a bar chart, but you shouldn't be doing small, medium, large. It's not detailed enough. You need to be saying specific masses. So that is my statement there about the graph. I want to be really, really clear that I understand still, so I'm going to say a line graph of the height, the size of the diameter of the crater against the drop height. And what I'm showing there is I know the two pieces of data that need to go on that graph. So you can see there I've gone 1, 2, 3 marks for the different variables, 4th mark for the equipment, 5th mark for a nice detailed method, including ways to make sure that this is kept reliable the whole way through. I've also included repeats in there for my 6th mark, which is the hidden mark, and then my 7th mark is my graph. And I've been really specific about the type of graph and what's going on the graph. And that's it. That is my alternative to practical section. All alternative to practical sections that you see will be very similar to that. It's always the same kinds of questions. So make sure that you're really comfortable writing methods, interpreting data, and really just following instructions.